Okay, so where we left off with on Friday was we were introducing the concept of functions, how we define a function to be a set of ordered pairs such that no two ordered pairs in the set have the same x coordinate and different y coordinates. And we specifically are going to be referring to what we call linear functions, and that's primarily going to be what we focus on in section 1.3 pretty soon. But the last part of section 1.2 that we want to talk about is how we find what's called the domain and the range of functions. And by definition, the domain is the set of all possible x values for a function. And the range is the set of all possible y values. In general, it is easier to find the domain than it is to find the range. In order to find the range, you have to know something about the graph, about what the nature of the function, what it does. The domain of the function, well, we have two questions that we can ask ourselves to determine what the domain is. Now, even though, let me skip forward a bit. Okay. So we're going to start with finding the domain. And the only time that, for now, that I'm going to ask you what the range of a function is going to be a function where I give you the graph and I ask you to find the range. And we'll see a problem in just a moment where if the graph is given to you, the domain and the range, there's no calculation to do. You can read it right off the graph. When we get to quadratic functions and rational functions, then we'll start turning our attention to domain and to the range of those functions. For now, we're going to focus on how we find the domain. So when finding the domain of a function, for the functions that we are going to be encountering, there are two questions that we are going to ask. Now, this does not apply to every possible function. There are functions such as the logarithmic function, which we'll see in chapter 5, that doesn't quite fit this rule. But for the primary functions that we're going to see, these two questions will be sufficient to identify what the domain is. And the first question we want to ask is, does the function have any fractions with the variable in the denominator of the fraction? Not the numerator. Numerator doesn't matter. Is there a variable in the denominator? The reason this is important is because if there is a variable in the denominator, that means we're not sure what that denominator is. And if we're not sure what the denominator is, there's no real way we can be certain that it's not equal to 0. Because 0, you can't divide by it. You'll get an undefined value. So whenever you have fractions with x in the denominator, we have to be aware that x, or whatever the variable is, cannot take on a value that causes that denominator to be 0. The second question we're going to deal with is, are there any even roots, such as a square root, a fourth root, a sixth root, with the variable under the radical sign? And the radical sign is just the name of that square root symbol. Now, odd roots do not count. You can take for example, you can take a cube root of -1. The cube root of -1 is -1 itself. But if you have a square root of -1, now you've got a problem, because if the number that is under the radical sign, if that number is negative and you try to take a square root of it, you're going to get a complex number. It's going to be imaginary. And when we're talking about domains of functions, we're only focused on real values. So I need to be certain that the values of x that I plug into the function give me numbers that aren't imaginary. And we're going to look at examples of both cases. So if I have a function, well, first off, If the answer to both of those questions is no, their domain is all real numbers. Again, we're going to see an example later on in the semester. Logarithmic functions is going to be the only exception to this. Well, piecewise functions too, but we'll see piecewise functions in chapter 2. But in general, if we ask those two questions about that function, and both those questions are no, all real numbers is a pretty safe bet for its domain. So if I'm given this function, f of x equals 3x squared minus x plus 1, the instructions tell me to find the domain. I'm going to look and see, are there any fractions with x in the denominator? No? Are there any square roots, fourth roots, sixth roots that have x under the radical sign? No. In this case, there's just no real work for me to do. After I've answered both those questions, the domain of that function is said to be all real numbers. And get used to seeing domain and ranges expressed in interval notation as opposed to writing it out in words. If you're not familiar with interval notation, it is a very simple task. You can go on like a website like Khan Academy. Even your textbook should have a section that talks about interval notation. If you just search interval notation in a search engine, it's going to be one of the top results. It's going to be exactly what you're looking for. But for this function f of x, its associated domain is all real numbers. What is its range? We don't care right now. The question didn't ask that. When we get to chapter 3, we'll be able to give a very good answer for what the range is. Now, a problem that's a little less trivial. Here, I do have a fraction with x in the denominator. So now I have some work to do. I need to ask myself, what values of x, basically what I'm doing is, what values of x cause division by 0? So whatever that denominator is, set it equal to 0, and then that will give you an equation to solve. And the values of x that you get here will be the values of x you cannot allow to be put into the function, because you'll get an undefined value. So for this problem, the only number that causes division by 0 is 4. So my domain for this problem is all real numbers, except we're going to throw 4 out. And in the interval notation, that looks like this. So we're still going from negative infinity to infinity, but at 4, notice we're using parentheses in both cases. Parentheses mean that you include all numbers up to 4, but you don't include 4 itself. So this interval of numbers is all numbers less than 4. This interval is all numbers bigger than 4. And this symbol, which sort of looks like a capital U, but it's a symbol for union. All this does is it says that our domain is not this set or this set. It's the two of them linked together. But you can't just, they're split apart. There's a gap between them, a one value gap between these. So if you have division by 0, then you're going to have to remove the individual values that cause that to happen. Okay, so I wasn't sure how that orange would show up, but here is a function. Now, don't worry about what the function itself is. This graph would be what's called a piecewise function, and we'll see it in the next chapter. But for this kind of function, I want to know what is the domain and the range. So here we're going to answer both parts of it. So when you have the graph of a function, there is nothing for you to calculate. The domain is essentially the left-hand boundary of the graph up to the right-hand boundary of the graph. So in this picture, that red shaded region is the set of all x values that have a function point somewhere. We don't care where that function value is. But if a number, imagine if this line just extended out infinitely to the right. If I took a value that is outside of that red interval, notice there is no function value above or below for it, so it's not in the domain. But that entire red interval is the domain for this given function. So I can say that, now, again, notice I didn't mark the numbers, so I'm counting up by 1. So that red interval starts at what number? -4? And I've got a closed bracket over there because this circle right here is closed in. I want to make certain that I include that left-hand endpoint. Now this right-hand endpoint is an open circle. That is why it has a parenthesis here and not a bracket. So the domain in this case is going to be -4 up to +6. Just don't include the 6. And in interval notation, that's what it looks like. It sort of looks like an ordered pair, but this is not an x-coordinate and a y-coordinate. This is where the interval starts, this is where the interval stops, and this comma says that you're picking up all the numbers in between. The bracket says you include the left-hand endpoint, the parenthesis says you do not include the right-hand endpoint. Now to do the range, it's exactly the same thing we just did for domain. But instead of going from the left to the right, we're going to start at the bottom and work our way up. Notice that this graph, the lowest point on this graph, looks like it would be right here. But this point doesn't really exist. So this point is really, I intended it for it to be -2 on this, for this open circle. So the range is going to start at -2, but -2 is not included in it because this circle is not filled in. So the lowest point of my range is going to start right here, and it's going to go up until I reach the highest point of the function, which is all the way at the top at the point what looks to be about 1.5, 5. So if I shade that in, very similar to how I did for the domain, I'm going to get that. So my range, these intervals are always read from the lowest value to the highest value. So it would be wrong for me to switch these two numbers around. But this range is -2 to 5, but I want to include 5 this time because its highest point is actually filled in. This is how you just read the domain and range if you're given the graph. If you're just given the function, the range is a trickier question to answer. Now, one comment I want to make is, what if this open circle hadn't been here? What if this graph looked like this instead? Oops, let me take that off. It looks like this. Notice it doesn't look like I changed much, but what it looks like now is this line doesn't appear to stop. The only reason this line stops is because that's where the edge of my graph was. But this graph actually extends infinitely in all 4 directions. So if your graph runs, if the graph of your function runs right up to the edge of your picture, and there's no point there indicating that that line has stopped, you have to imagine that this line continues infinitely in this, whatever direction it was leading when it went off the edge of the paper. So in this problem, the domain, I still have -4 as my left-hand boundary. But now there's no right-hand boundary because it keeps going to the right, to the right, to the right. So the way we say that in this case is that the domain is -4. We just say that this is positive infinity all the way out on the right-hand side. For the range, yes, this graph is still going out to the right, but it's going down too. So there is no lowest point on the graph. It just extends infinitely downward. So my range is negative infinity because there is no bottom point. It goes all the way down to negative infinity. And I still have that highest point up there at positive 5. And the graph never goes any higher than positive 5. So I can cut it off right there. But that's how the domain and range would change if your graph appears to just disappear off the edge of the picture without there being a point there saying that the graph stopped. Okay, so we handled the case where the answer to both questions were no. We handled the case where the answer to both questions was, well, the answer to the fraction question was yes. Now, I have an even root in this problem. And I've already mentioned this, that the problem with square roots is that if that square root, if you're trying to take the square root of a negative number, you're going to get an imaginary value. So why don't we force that to never happen? If I take that 2x plus 3, whatever is under the radical, if I force that, if we force that value to be greater than or equal to 0, this ensures that that number is never negative. And I'll never be taking imaginary values when I take that square root. So whatever is under that radical, doesn't matter how complicated the expression, just take that entire expression, set it greater than or equal to 0. And this will tell you, when you solve this inequality, this will tell you what numbers you are allowed to keep. Any number that falls below negative 3 over 2 is going to cause that expression to be negative under the radical, and you will be taking an imaginary value when you evaluate that number. But this is how we'll handle the case whenever we're dealing with functions that have even roots in them. We can force that root to never return imaginary values. Now, what if, and I don't have, well, I can just go ahead and go to the next slide, I guess. So this is my domain right here. The set of all values greater than or equal to negative 3 over 2. And as an interval, let me get this out of the way, that cursor. As an interval, negative 3 over 2 marks the absolute smallest value. We'll take anything bigger than it, but it cannot drop below that negative 3 over 2. There may be a reason why this inequality switches direction. Like if this were a negative 2 right here, instead of a positive 2, when I try to get x by itself, I would be dividing by negative 2. And if you're familiar with your rules of inequalities, anytime you multiply or divide by a negative, what that will do is it will change the direction of your inequality sign. Well, it would apply here as well, but that wasn't necessary in this problem. So that would be the last set of problems you encounter in section 1.2, where you're given a function, what is its domain? And in the cases where the graph is given to you, expect the range to also be asked as well. Okay, so section 1.2 talks about functions in general. All functions have those conditions. You can find the domain and range using the technique we just showed. You can graph a function by plugging values of x to it and generating generating the y coordinates of those points. There are many different types of functions. There's linear functions, quadratic functions, cubic functions, polynomial, rational, radical, exponential, logarithmic, and that's just the ones we're going to see in this class. That's not trigonometric functions or anything like that. But we're going to turn our attention only to the most basic functions right now. In chapter 1, we're going to be focused on linear functions. And a linear function is a function of the form, if it can be written in the form f of x equals mx plus b. Now, I just want to mention that, remember that f of x and y are essentially the same thing? You can replace f of x with y and vice versa. These two expressions say exactly the same thing. So if I were to look at something like this, I would still view this as a linear function. And the condition is that m and b are constants. So x is raised to the first power. This would have said mx squared. It's not linear. And linear functions get that name because, predictably, their graphs are straight lines, always. Okay, so now m and b are constants, which means they're any real numbers. Positive, negative, fractions, zero, doesn't matter. But if m is equal to 0, what is 0 times x? 0, right? So you'll lose this whole term altogether. And what you will have is f of x equals b. If you have an equation of that type, then the value of x you pick is not going to change that number because the value of x is only in this part of the function. If this said f of x equals 2, well, it doesn't matter what value you plug into the function. 2 is the number that's going to come out. So we say that as a constant function because the y value is going to remain constant for all values of x that are substituted into it. There's also another special function, and that arises when m is equal to 1 and b is equal to 0. If b is equal to 0, you can just pretend it's not there. If m is equal to 1, what is 1 times x? What's 1 times anything?
Whatever x is.
Whatever x was. So if this is equal to 1 and b is equal to 0, then my function is going to become f of x equals x. This function is what we call the identity function, because the number that comes out of the function is identical to the number that went into the function. And I already made that comment that the graphs of linear functions are straight lines. So let's start by talking with horizontal and vertical lines. Horizontal lines are given by equations of the type y equals b or f of x equals b. Remember, we just called those constant functions on the previous slide. So if your graph is constant, its graph is going to be a horizontal line that has the y coordinate equal to whatever the function value said it was. Now, horizontal lines, if you just imagine a horizontal line and try to draw, and I'll sketch it down here. If I just take a horizontal line, it doesn't matter where it is. If I sketch just some vertical lines, do you see how all of those blue lines intersected the graph exactly one time? Don't count where it hits the axis. Count where it hits the graph. It only hits the graph once. So horizontal lines are functions. So let me back up and get that out of the way, because I need that room. So horizontal lines are functions. Vertical lines, however, are not. Because if you guys, your graph is a vertical line, then it's going to fail the vertical line test because it intersects itself an infinite number of times. And all a vertical line has to do is intersect your graph twice for it not to be a function. Vertical lines will intersect itself a whole lot more than twice. But we know what the equations of vertical lines look like. Horizontal lines are y equals a number. There's no x in that expression. It's y equals 2, y equals -3. Those are horizontal lines. But if there is an x with no y in it, then this is going to be a vertical line that has all of the points, like if you have x equals 2, all of the points on that vertical line are going to have an x coordinate of 2. Now the y values are going to be different. The y values can be any value. Like if I were to graph, let me put in a graph, a new page, so I can show you. If I were to, so here's my axis. This is x, this is y. And I want to graph the function, oops, it's not a function. I want to graph x equals 2. Well, I could plot some ordered pairs. Remember, this is what we were doing in section 1.1. We were plotting some ordered pairs. So if I let y equal 0, for instance, if I let y equal 0, what does that equation say x is equal to? 2. Now you may be saying, well, there's nowhere for me to substitute y in it. That's precisely right. In other words, the value of y you pick is not going to influence the value of x. So if you pick y is equal to 0, well, the equation says your x value is equal to 2. Pick another value for y. Okay, your equation says the x value is 2. And you can just keep doing that. Even though y is not in the equation, you can still pick values for it. It's just not going to contribute to what the value of x is. And if you were to plot those points, here's x equal 1, here's x equal 2, 1, 2, 3. So if I were to plot these points, here's the point 2, 0, here is the point 2, 1, 2, 2, 2, 3, and I can't draw vertical lines very well in this without a straight edge, and I don't have one. But if you were to connect those lines with a straight line that connected and went through all the points, it's clearly going to be vertical. And vertical lines are not functions. They are the only straight lines that are not functions. Horizontal lines, yes. Diagonal lines, absolutely. Vertical lines, never. Now, in section 1.1, when we were talking about ordered pairs, as soon as we put 2 points in the plane, one of the first questions we asked ourselves was, okay, now that we have 2 points, how do we find the distance between them? And then we said, now that we have 2 points, how do we find the point in the middle of them? So that gave us the distance in the midpoint formulas. However, if you have 2 points in a plane, then you can draw a line that connects those 2 points, and then we can talk about a property that that line has called its slope. Now, a slope is a measure of the line's steepness. Do y'all remember what slope is? How do y'all typically remember slope? Rise over run. There are some things about math that they just gel with students and it sticks in their mind and they keep it their entire lifetime. Slope equals rise over run happens to be one of those. So what I'm going to do is I'm going to take these 2 points, and if they're labeled this way, and it doesn't, again, just like in the distance and midpoint formula, all that matters is that the subscripts match. It doesn't matter which one you call x sub 1 and y sub 1 and which one you call x sub 2 and y sub 2. But rise over run is defined to be y sub 2 minus y sub 1. Because if I take y sub 2, which is the height of this point, and subtract out y sub 1, which is the height of this point, what I'm going to get is the vertical distance between those 2 points. It's going to give me the rise, or how much this point has changed in vertical position from going from here to here. In this case, it went up as we go from left to right. But it's possible for it to go down or for it to go straight across. But that is our formula. And y'all are keeping a list of formulas that you got to know for the test, right? Add that to it. So now you have 4. You have the distance formula, the midpoint formula. You have the equation of a circle, and you now have the slope formula. So long as you know 2 points on the line, and you do your arithmetic correctly in the formula, you'll get the slope. So if we're asked to find the slope of the line containing the points 9, 4, negative 1, 2, well, we're going to start by labeling our 2 points. And then once we've done that, just plug them into their respective places in that slope formula. And just like in the distance formula, it's important to remember that, of course I'm talking, that there is a negative sign in the numerator of the slope formula and in the denominator. If x, for example, if that would have been negative 9, 4, I would have to take negative 1 minus negative 9. And that negative would switch that back to a positive. So it is very, very easy to be working a lot of these problems and then just get careless and lose a sign somewhere. It happens all the time. So just be aware of it and be very watchful of your signs when applying these formulas, especially the ones that have negative signs in the formula itself. Now, what does this tell us? This tells us something about the graph. Because if a slope is positive, then as you read the graph from left to right, the graph is going to be pointing up. So there are 4 cases. And there they are. Now, this black horizontal line and this black vertical line, those are not x and y axes. I'm just breaking my screen up into 4 pieces. I've got 4 graphs here. All of them have straight lines. One of them has a slope that's positive, one of them has a slope that's 0. One of them has a slope that's undefined, and one of them has a slope that is negative. If a line is going up from left to right, like it is in the upper left-hand corner, that slope is positive. And the closer that line is to vertical, the bigger that number will get. Now in the upper right-hand corner, as you go from left to right, the line is going down. That is indicative of negative slope. The 2 graphs at the bottom are the special cases, the horizontal and vertical lines. For this vertical line, we said this was not a function. Well, if you try to calculate its slope, what's going to happen is that denominator of that function, go back to the slope formula and look at it. The denominator says x sub 2 minus x sub 1. If I take 2 points on the vertical line, their x coordinates are the same. So if their x coordinates are the same, what is x sub 2 minus x sub 1 going to be? It's going to be 0. And that will be the denominator of that fraction. You're going to get an undefined value. That's why the slope of vertical lines is undefined. Now, for horizontal lines, going from left to right, the line neither goes up or down. Remember, slope is a measure of a line's steepness. If it's not going up or down, we say that its slope is 0. We do not say that it does not have one. The only one that you can make that argument for is the vertical line, and its value, it doesn't have a value, it is undefined. But labeling these properly, that is how, well, what you should remember when you see graphs of functions. So if I tell you that I am thinking of a function whose slope is positive 4, I haven't told you anything about the function itself, but I have told you something about the graph. Yes, sir? Oops. Perfect. Yeah, thank you. I still have a little space at the bottom of my screen, but this is right at the bottom of the projection. So. Okay. Now we said that linear functions had the form f of x equals mx plus b. There was a reason we used because is the letter we use for slope. Now why was used instead of s? Because was chosen from the same word that we derived the word mountain from. That's why it was from whatever Latin word that was used for that. So the slope is, anytime you see a linear equation that has present in it, is reserved for the slope. B is going to be not the x-intercept, the y-intercept. So this is what we refer to as slope-intercept form of a line. Because if it's written this way, we can just read what the slope and the y-intercept are, and it doesn't require us to use the slope formula. So here's a function, g of x equals negative 2/3 x plus 4. What I want to know is what is its slope and its y-intercept. This is one of the cases where, so long as you know what the numbers represent, there's no calculation for you to do. Once we pull the numbers out and put them in the right places, then the slope is whatever the coefficient of x is. And this is important to mention, because if I would have written this function like this, g of x equals 4 minus 2/3 x. If I look at this function, what is the slope? It's not 4. It's still negative 2/3. This is what you've got to be careful with. The slope is whatever number is attached to the x. Okay? You will see this happen on my math lab sometimes. So typically, linear functions are written in the form of mx plus b. But 2 plus 3 is the same as 3 plus 2, right? So you can switch numbers around so long as you take the sign with them. So negative 2/3 x plus 4 is the same as 4 minus 2/3 x. So the slope and the y-intercept should be the same. Okay, so that's